Okay, the next speaker is Gagliardi.
So I want to start by thanking the organizers for the invitation to come. When I first got the request from Steve, my comment was, I wasn't one of Willy's students, and I wasn't in Willy's academic chain. I was in a different academic chain. But Steve commented that on the one hand, he wanted to show that what Willy's developments really have evolved far beyond the work that Willy himself performed. But on the other hand, I recognized, maybe better than Steve realized, that Willy had had an impact on my career. The good part of Willy's impact on my career, Steve knew about. The other part of the impact Steve didn't know about, but I thought I'd take a few minutes and tell you about it. So I never collaborated with Willy. In fact, this is the first time I've ever been in Madison. I'd driven past on I-94 a couple of times. So Willy and I only bumped into each other and chatted at conferences. But it turns out that on the one hand, his pioneering work on polarized atomic beams, he was the god of polarized beams after all, had a huge influence on me as a young graduate student. And there is absolutely no question that without the tools that Willy developed to measure absolute polarization of the RIC beams, and we heard about that in a couple of talks yesterday from Tom and Yusuf, much of the past 20 plus years of my career, including all of my work on gluon polarization, which was the topic that Steve specifically asked me to talk about, would have been completely impossible.
It's my fault. Just give me a second.
No problem.
Yours.
Okay, so let me take a few minutes and tell you a story that I think nobody in this room knows. Only if you were at Argonne in the late 70s would you know this story. I've actually never told this story at a meeting before, and you'll come to understand why. It's the description of the dark days of my career. And they turned even darker.
I'm sorry. Thanks for your patience.
No problem, no problem. Okay, so it all starts with a parity doublet in boron 10. It's a 2 plus 2 minus doublet. They're only 54 keV apart. It's just a little above the lithium 6 plus alpha threshold. And it's an isovector parity doublet. And mixing between these two states would actually be sensitive to the isovector pion exchange contribution to the weak nucleon-nucleon force. We heard from Thomas Roser about the parity proton-proton and proton alpha parity violating experiments at PSI, at SIN in those days. One of those was insensitive to the pion exchange contribution, which is the only long-range piece of the nucleon-nucleon force. The other had some sensitivity, but this particular parity doublet provided direct sensitivity. The only other experiment system that did that was fluorine 18 that had a null result at the time. Understanding the two nucleon weak force was a very hot topic in the mid-70s. And it could be probed via parity violating single spin asymmetry for populating that 5.16 MeV state. Note that the 5.11, this is an isospin allowed L equals 1 transition. The 2 plus is an isospin forbidden L equals 2 transition. So the alpha width of the 2 plus state was only 0.3 EV versus a KEV. If we populate the parity violating 5.16 MeV state, we get a nuclear enhancement of over a factor of 50 from those widths. We have a very small energy denominator, so a relatively small weak matrix element could correspond to a measurable signal. It does require longitudinally vector polarized lithium-6 target. This actually looked like it should be straightforward, because when I was a first-year graduate student, the first measurements with a polarized lithium-6 target were published. Hamburg at the time had a polarized lithium-6 beam. It was an atomic beam. They ionized it on a tungsten surface ionizer. And they had the clever idea that the lithium ions sit on the surface ionizer for a period of time. During that period of time, they could constitute a target. So they used that and irradiated that as a polarized target. High polarization, thickness 3 × 10⁻14. Well, with 3 × 10⁻14 lithium-6 per square centimeter, and the absolute cutting torch alpha particle beam intensities that were available in those days from the argon dynamitron, an interesting measurement could be done in 2 to 3 weeks. Of course, more would be better, but an interesting measurement was doable. And as soon as I finished my Princeton general exams, I headed out to Argonne to get going on this experiment, starting from a green field. I devoured all of Willy's papers on polarized deuteron beams, because after all, lithium-6, as far as spin, is just a heavy deuteron. I also studied the Hamburg system in detail. Jerry Garvey, who was one of my 2 advisors, my other advisor was Stuart Friedman. Many of you knew both of them quite well. Even arranged to have a dissertation from Hamburg translated from German for me. There were some amusing things in that translation, because the person who translated it obviously didn't know any science. Over the next 2 years, I built an atomic beam. This part, this is actually the Hamburg system. I don't have a figure of my beam. Was very much like a standard deuteron atomic beam. What would be a dissociator up here is an oven for lithium. This part I designed rather similar to Hamburg, but I had a better oven. It was modeled after one at SLAC that was used for early polarized electron beams before gallium arsenide. They also had a fire with that oven. So we had to worry about avoiding it. I had much better sextipoles that I inherited from the atomic physics group at Argonne. And I spent 2 years building it in a lab off beam. And it worked great. High intensity, we estimated we had enough to get up to 10⁻15 per square centimeter, 3 times higher than Hamburg. That would be a monolayer. That was our goal, because we figured beyond a monolayer, things would start to depolarize. But if we could get to a monolayer, great. If we ended up at 3 × 10⁻14, still great. Vector polarization was very close to -1/3. I only had a weak field transition unit because I wanted vector polarized beams and I wasn't interested in the tensor polarization. So in 1979, it got moved out of the offline lab and installed on one of the dynamitron beam lines. But beam measurements showed that the target thickness wasn't stable at 10⁻15 per square centimeter. If I set it up and tuned it for 10⁻15 per square centimeter, the target thickness would then continue to grow, and the polarization went to hell in a handcart. So I backed off to 3 × 10⁻14, and I had the same problem. And I backed off to 1 × 10⁻14, and I had the same problem. Jerry tried to contact the Hamburg group to understand what they were doing right, and I was obviously doing wrong, and received no reply until August of 1980, when the 5th International Polarization Phenomena Symposium was in Santa Fe. I was not there, and it's too long ago. The mind is gray. I don't remember whether Jerry was there and heard and spoke with them, or if they simply provided us with a write-up immediately thereafter. But from their proceedings, the target thickness was 10⁻13 lithium particles per square centimeter, corresponding to a surface coverage of 1/100th of a monolayer. It will probably not be possible to thicken the target essentially by an enhancement of the atomic beam intensity. There was no discussion of the factor of 30 difference between what had been claimed in the previous paper. In fact, the previous paper wasn't even referenced in the proceedings, even though the authors are the same. At 10 to the 13th, the measurement would take years of beam time instead of weeks. But I'd put 3 years of my life into the damn thing. Somehow I was going to make it work. So I continued to bang my head against it until 8-10 months later, I don't remember exactly when, sometime in spring of 1981, Jerry was tired of watching me bang my head against walls. So he declared he was pulling the plug on lithium-6 alpha gamma over my very strong protests. He asked me if I wanted to write up a hardware dissertation talking about everything I'd done, what worked, what didn't work, what I'd learned. I had absolutely no desire to do that. I told him I wanted to write a dissertation about an experiment that worked, not one that failed. So after 4 years, because this was now spring of 81, 4 years after I'd headed out to Argonne, I started over on a completely different experiment. The different experiment, interestingly, also involved pion exchange contributions to the weak current, but this time it was weak current in beta decay instead of the weak current in the 2-nucleon force. You know, if you have a highly motivated graduate student, things can happen quickly. And after 4 years of hell, I was highly motivated. Designed a completely different apparatus, took the data, analyzed it, wrote the first paper, took more data, wrote my dissertation, and defended in June of 1982. And oh, by the way, between taking more data and writing my dissertation, I met my future wife. That year was an amazing year, probably the best of my life after the 4 years of hell. Shortly thereafter, I left Argonne for Texas A&M. And at that time, discussions were underway about possibly moving my lithium-6 atomic beam here to be installed as a polarized ion source for the tandem. I never heard anything after that, so I assume it didn't end up happening. But if in fact it's somewhere in the building, I would love to see it. You might not know it, but it would look like when the vacuum chamber is closed, it would look like a big stainless steel doghouse. I assume it never left Argonne. So once I got to Texas A&M, I did all sorts of various nuclear physics experiments. I stayed away from atomic beams. Even though the atomic beam had worked great, it was actually condensed matter surface physics that had screwed up my efforts for lithium-6 alpha gamma. Until 18 years later, when after some lobbying actually by Steve, I joined the STAR experiment at Rick to try and understand what makes the proton spin. And Willy and his atomic beams re-entered my life. And this time things went well. So most all of us are of an appropriate age to remember the static quark model. And a homework problem that I was given in nuclear physics as a young graduate student, and probably many of you were too, was to write the wave function of the proton in the static quark model, and then use it with constituent quark masses, because that's what we had in those days, to calculate the magnetic moment of the proton, the neutron, and the ratio, and it all worked stunningly well. And at the time, this was considered a great success of the static quark model. But as we all know, and for example, as Richard showed in the previous talk, the proton is actually a highly dynamic object. We don't talk about a static quark model any longer. We talk about part-time distribution functions. This is an old plot. I'm sure that Elka will complain at me about how old it is, but it's one I have available that's easy to grab, of deep inelastic scattering data and the curves that are the part-time distribution functions fits, giving us the probability of finding a quark or gluon in the proton carrying some fraction of the total momentum of the proton. Find more glue than anything else, and the gluons carry half of the momentum. Of course, this immediately begs the question, what about the spin? Well, we can also have polarized parton distribution functions. And the first measurement that looked at them over a broad kinematic region was by the European muon collaboration back in the mid 1980s. They measured the G1 structure function, these solid points. They integrated from various x values up to 1, and the integral from the x min to 1 seemed to saturate at about 0.115. It's a number. The surprise was it was supposed to be up here at 0.19. And the net result was that it concluded that quarks contribute about 14 plus or minus 9 plus or minus 21% of the proton spin. This came to be the origin of the proton spin crisis. One of the possible explanations involved surprisingly large contributions from strange quarks, and that generated a lot of interest in strange quark form factors that KK was telling us about this morning. Well, after 2 decades of measurements from there, 2 decades because this is actually a 2008 paper, there were many, many subsequent measurements, and the results are very well described by global analyses that find best fit polarized parton distribution functions. This is just a tiny fraction of the data that were fit in this particular paper. The distributions for U plus U bar and D plus D bar are actually quite well determined by deep and elastic scattering. The individual quark flavors are not as well determined, and that's a completely different Rick spin talk than I have time to give today. Bottom line is ballpark 30% of the proton spin arises from quarks and antiquarks. That leaves a lot of spin to be found elsewhere in the proton. What about gluon polarization? Well, the unpolarized bits have access to a huge body of data. The polarized bits are far more limited. They live down in this little triangle, and there are far fewer points per unit area in the triangle. But the biggest issue for gluons is that gluons are determined here from evolution, as Richard was commenting, basically from measuring the slopes of these curves. And when the curves get truncated early, it's really hard to measure the slope. So to set a scale, here are 2 global analyses, both of which were published in 2010. And this is the gluon polarization that came out of them. This fit included only inclusive deep and elastic scattering data. And in units, this is in units of h bar. So this says that the gluon contribution to the proton spin equals a half h bar, the proton spin, plus or minus a half h bar, the proton spin. This fit included deep inclusive and semi-inclusive deep and elastic scattering data, found 2 best fits. One where the gluon polarization is positive at all x values, and it contributes 2/3 of the spin of the proton, plus or minus 40%. But it also found a second fit with a node, and actually there's more glue down here at negative with negative polarizations than up here. So this one found that the gluons contribute 1/3 of h bar with the wrong sign, plus or minus half of h bar. Obviously, all of that deep and elastic scattering data over 20 plus years doesn't tell us what we need to know about the glue. In fact, we have a parse separation where the deep and elastic scattering tells us the quarks, glue is poorly determined, orbital angular momentum, not at all. Enter Rick. Rick was built with 3 goals in mind. The most important one, as far as I'm concerned, is to explore the partonic structure of the proton. Rick has 2 large general purpose, or had 2 large general purpose detectors, and will again shortly. The Phoenix detector, which has since been disassembled and is being replaced by a new detector, S-Phoenix, and the star detector. Truth in advertising. My colleagues in Phoenix have done lots and lots of great work over the time, but I am not an unbiased observer. I am a member of the STAR collaboration, and I'm absolutely convinced that STAR is, has been, and always will be the star at Rick. Thomas told us all about the Rick ring yesterday. Let me just say that from an end user perspective, the ability to choose the spin pattern RF bucket by RF bucket and change that spin pattern from fill to fill, which are sort of 8-hour periods, is an incredibly powerful tool for suppressing systematics. And let me credit the accelerator people, the spin dynamics in the Rick ring are stunningly well understood. With the two Siberian snakes, the spin gets flipped twice in every rotation. And in an 8-hour fill, that means that the proton spins are flipped literally billions of times. And if we're running at a center of mass energy of 200 JeV, we might go from 60% polarization at the beginning of the fill to 59, or in a bad day, 58% at the end of a fill. If we're running at 510 JeV, we might start at 55 and end at 52. The spin dynamics are really, really under exquisite control. But there is this thing up here, absolute polarimeter. That's the H-jet that Tom talked about and that Yusuf talked about yesterday. Without that, there would be no Rick spin program, because without that, we wouldn't know the absolute polarization of the beam, and you can't measure spin asymmetries. If you don't know the polarization, you just get P times A, and you don't know how to slice and dice that. So all of the physics that I have done in the past 20 years at Rick have depended essentially on that absolute polarimeter. And you saw this, actually you saw a picture of it yesterday. There's Willy, there's Yusuf, there's Tom. Incredibly powerful tool, essential for all the work. So what makes PP different from deep inelastic scattering? Richard was talking about deep inelastic scattering a moment ago. In deep inelastic scattering, this is an electron and this is a photon, and it couples as electromagnetically to charge, so this has to be a quark. At Rick, where we have PP collisions, we have a proton and another proton. We pull a parton from each of the two protons, and then they interact through the strong interaction. And that means that the partons we draw can be quarks, just as in deep inelastic scattering, or they can be gluons, or a combination. And that means that gluons contribute at leading order, not just at higher order in PP collisions. The star measurements I'm going to show involve detecting one or both of these outgoing jets. We've done other things, but these are the ones that have been most discriminating. The Phoenix measurements I'm going to show involve mostly detecting one energetic hadron fragment from one of the jets, typically a pi naught. They've done other things, but these are the ones that have been most discriminating. Oh dear. When we explore gluon polarization at Rick, we're measuring the longitudinal double spin asymmetry. That's the difference divided by the sum for like helicities and unlike helicities. It's proportional to the product of the polarized parton distribution functions divided by the unpolarized parton distribution functions times the spin asymmetry at the partonic level. And for gluon-gluon scattering, that's red, and quark-gluon scattering, that's blue. The asymmetries, especially near mid-rapidity in the parton-parton frame, are quite large. Furthermore, if we look at the cross-sections at Rick, blue-blue scattering dominates at low energy or outgoing momentum. Quark-glue at intermediate, quark-quark only dominates when you get up so high in energy that the cross-section's gone to squat. And in turn, over essentially all of the Rick kinematics, glue-glue and quark-glue dominate the cross-section. They both have large spin asymmetries, and the bottom line is that ALL for pions and jets is sensitive to gluon polarization. We had a modest beginning. This is the first measurement sensitive to gluon polarization from Rick. It's a Phoenix paper from 2004, based on a small data set that was recorded in 2003. The beam polarization at the time was estimated to be only 27%. It disfavored this curve here, GRSV max, which was a kind of a crazy model. It was a model that assumed that every gluon in the unpolarized parton distribution function had its spin pointing along this proton spin direction. That ended up adding up to something like 2 h bar, which then required all sorts of swirling orbital angular momentum to cancel it to get back down to a ½ h bar for the proton as a whole. It was also disfavored by DIS, but only at about the 2 sigma level at the time, indicative of the fact that DIS wasn't particularly sensitive to the gluon polarization. This was the very first measurement. There were a number of other measurements over the next couple of years that led to the first global analysis that included the RIC data, and it was done by the DSSV group in 2008. Here are their fits to the Phoenix and STAR data that existed at the time. The solid, the open squares are actually 2005 data. The open triangles are 2006 data. And in both the cases of Phoenix and STAR at the time that this fit was done, those were still preliminary. Here you see the fit to the experimental data. Here's the gluon polarization that they concluded. Note that this dashed curve here, that's that GRSV max scenario. This dot dashed curve for scale is that solid curve. So obviously the gluon polarization is less than that solid curve. In fact, the integral of the gluon polarization in this particular fit came out very close to 0, but with still a large uncertainty. We took data the next year, 2009. This is still before those theory papers that I showed you from 2010, both from Phoenix and from STAR. Took data in 2009, analyzed them, and released final results in 2014. Far more precise than any previous results. Here you see the Phoenix pi-naught ALL compared to that dashed curve or dashed dot curve there, which is that line there, and the green error band is the error band here. Here are the STAR results compared to the DSSV is this green dashed curve here. The red, blue, and purple curves are from those gluon polarization fits that I showed you earlier, and the cyan is from the NNPDF group that had come up in between the two. For scale, if I take this yellow uncertainty band and I overlay it here, it goes from just below the red curve at the top to basically the horizontal axis at the bottom. The bottom line is the data drew a very narrow road through the pre-existing uncertainty band. And it furthermore sat systematically above the dashed green curve, which had delta G of 0. This by eye immediately said the gluon polarization is positive. Fits were done very quickly by both the DSSV group, a new fit there, and a fit by the NNPDF group. They both found that the RIC results provided significantly tighter constraints with evidence for positive gluon polarization in the region X greater than 0.05 at the level of 3.5 standard deviations. But we still had much to learn. This is the uncertainty budget from this fit. Here is the integral from 0.05 to 1, and there is that uncertainty range, the 0.19 plus minus at 90% that I commented. But note the integral from 0.001 to 0.05 goes from minus 0.3 to plus 0.8 h bar. This proton spin is here at plus 0.5. So obviously, we need to extend the sensitivity to lower X values where the extrapolations have very large uncertainties because there's lots of glue down there. And a small fractional polarization of that glue could add up to a big contribution to the spin of the proton. We also need increased precision in the sampled region to consolidate the observation. We're still only at the 3.5 sigma level. STAR took data to probe this in 2015. Phoenix chose to run transverse that year, so they did not take any data for that, but the higher energy measurements were done by both Phoenix and STAR in 2012 and 2013. So here's collected mid-rapidity data. The blue is the 200 JeV that I just showed you. The red is the new Phoenix data from 500 JeV. The gray points are the STAR 200 JeV data that I showed you, and the other three colors are the green is more 200 JeV from 2015, the red and the blue are 500 JeV from 2012 and 2013. Everything is in pretty reasonable agreement with that 2009, with the global analyses from the 2009 data, but the blue points here and the gray points here are the only ones that have ever been included in a global analysis. There's a whole lot more data now. We need a new one. STAR has also published dijet measurements. Dijets enable direct reconstruction of X1 and X2 at leading order on an event by event basis to constrain the X dependence. For example, for one particular momentum bin, where the inclusive jet measurements is this gray, big wide blob. Dijets for one kinematics give a narrow peak here, and another kinematics, we get two narrow peaks, and we get the asymmetries. Now, dijets, this is really cool, but note that the gray inclusive jet is divided by 20. So statistics wise, inclusive jets clearly win. The blue are 2009 data and the green are 2015. We've also published now where we've moved one particle forward. So I've got, I think, 2 slides left. So where one particle goes, so if the beam is coming here, we look at one jet that's coming off here, and then we look at a second jet here, then here, then here. If both jets come off this way, then you had a very asymmetric collision with an energetic parton this way and a soft one this way. You see that this is this combination, this is this combination, this is this combination, and you see how the low X parton just moves down and down. Here's the data. We actually have similar measurements at 510 JeV that'll provide sensitivity below 0.01. They're preliminary right now. And the DSSV group has performed a global analysis, including these data and these blue data. But these green data and all of the 500 JeV data, which are all analyzed and published, have not been done. Phoenix recently submitted a direct photon asymmetry. As you can see, the uncertainties for the direct photon are large. The statistics are limited. But 90% of the cross-section arises from quark-gluon Compton scattering. So it's a very pure probe for gluons, and it'll have different systematics from pi naught and jet measurements when included in a global analysis. And with that, let me conclude that deep inelastic scattering has measured the polarization of the quarks. Thanks to Willy, Rick has shown us that gluons in the proton are also polarized and might actually contribute as much or more to the proton spin as the quarks do. And Rick is also making major contributions to transverse spin structure, those transverse momentum dependent things that Richard talked about in the last talk. And Willy has been essential there too. But Rick can't tell us much about gluon polarization at very low X, nor can it tell us about parton orbital angular momentum. So that's why we're looking forward to the electron ion collider to fill in those last key pieces. And I assume we'll be hearing about that from Elka next. Thank you.
Thank you. Thank you, Carl, for a very engaging talk. Questions? Tom Wise. Can I pass this behind?
So, Carl, lithium source came to Madison. We got it working. We put it on the tandem and made lithium-6 polarized beam. And I think there's a paper written on the data taken from that.
I didn't find that. I looked.
Yeah.
Is it still here?
No, it got taken out. It's not, no, it got scrapped eventually.
Okay. I looked and I didn't find it, so I didn't do the right search. Because I really wanted to have a paper from it having been moved here and used for an experiment as the end of that part of the talk, but I didn't find it in a 5 minutes search. I didn't do a detailed one. It's coming.
Hi, Erd Steffens. In fact, I'm from this group which produced for you the bad experience with lithium-6 target.
Your name is never on any of those papers.
Sorry?
Your name was not on any of those papers.
Not in this, on this paper, but of course I also developed this source. And then I went to Heidelberg, to the Max Planck Institute. We had a program of polarized heavy ions, so lithium-6, lithium-7, and even sodium-23.
Also.
Yes, and when I hear, I mean, know about your experiment, but I'm expert in surface ionization at least at that time. I suspect that when you put beam on this hot tungsten filament, it got too hot. And then the lithium disappeared simply.
The lithium absolutely did not disappear because we saw the cross-section. We actually saw the target get thicker. It was not disappearing, which is what I was expecting.
I mean,
I was very surprised by that.
if the layer got thinner, then it means it's disappeared from the surface.
Well, but our problem wasn't that the lithium got thinner. Our problem was that the lithium would build up. It wouldn't stay stable at a particular thickness. It would grow.
It's a question of temperature.
That was
But,
one of the variables I adjusted many times very carefully. I had lots of control over both the oven and the ionizer.
You should have asked me.
I probably should have. And as I said, it worked great in Hamburg and you know, as a polarized
How
beam.
much beam power? I mean, to measure the polarization of this surface layer, how much power did they put on this filament?
As I commented, the dynamitron could in principle produce a milliamp, but it could also produce nanoamps. The dynamitron was an amazing device for that kind of thing. My actual dissertation experiment, I think I had a 2 milliamp deuteron beam, I think, to make the nitrogen 16.
Okay, if there are no more questions, let's have coffee. We reconvene here for Elke's talk at 3:30.